Mm.
So, hi everyone, welcome back to Toronto AI Seminar. Today it's our pleasure to have Ivan here to present his research on generative model for neural field. Ivan received his PhD degree from Carleton in March 2023, where he was a part of Visual Computing Center supervised by Peter Wonka and Peter Mahanan. He does deep learning research and includes generative model and neural rendering. Before that, he was a deep learning researcher at MIT for 2 years. He first worked on NLP and then on loss landscape analysis. Before joining MIT, he was a software engineer at Yandex for 1.5 years. So yeah, uh, it, um, we're all looking forward to your talk today. So the stage is yours.
Thank you. Thank you for introduction. Thanks for inviting me. Okay, let's get started. So the main theme of my today's talk is generative models for neural fields. It is a topic which I have been working for the past 2.5 years, I would say. And we will cover several topics along the way, subfields, I would call them. So basically, first we'll start with some background, and first let's see what neural fields are. Basically, neural fields, it is just a new way to represent data as neural networks. For example, for images, a traditional image representation, it is RGB array. It is a grid-based, array-based representation, which is discrete and contains color values. So you are all familiar with it. And so there is an emergent paradigm, which is now quite popular, especially in 3D, and it represents images and other signals as a neural networks. And the information about the image is encoded in the parameters of these neural networks. And under the hood, it is a neural field is just an MLP, which takes a coordinate as an input and produces an RGB color for images, for example, or occupancy for 3D shapes, or also RGB color for videos, but we also have the temporal axis for them. And we can also represent sounds as neural networks, where we have just a single input coordinate, and we predict we output the amplitude in this location. And for 3D, there is also so this was the basic intuition behind neural fields, and for 3D, you need to add some additional extension, because for 3D, typically signal and measurement spaces are different. What that means, so we would need to add an additional notion of a forward map to unify all those signals, all those 3D representations under the paradigm of neural fields. And the very general framework looks like this. So we have a coordinate space, and the coordinate goes through the positional encoding, which is most often a sinusoidal function, or recently there started to be popular grid-based positional embeddings, for example, instant NGP. I guess it is the most dominant now for 3D. And then this positional embedding is input to the neural network, which predicts the value in the signal space. And most often we are unable to have any supervision in the signal space, because our measurement space is different. That's why we convert the values from the signal space to the measurement space. For example, for 3D shapes, it can be done with sphere tracing. And this is what people typically call as a forward map in the general neural fields framework. And then we go into the measurement space. Basically, this pipeline, it depicts neural fields. And again, it is just a way to represent signals as neural networks. And another introductory slide is on GANs. So I guess everyone, so it is a popular framework for synthesis tasks. And I guess I'm sorry if you're already familiar with it, but I would still cover it just in case. So basically we have two neural networks which are trained simultaneously. The first one is the generator, which takes random noise as input and predicts, so for images, it predicts the samples of your data set from random noise. And we also have real samples. And the other network is the discriminator, which is trained to classify the samples onto real and synthetic or fake ones. And the final built-in block, which we would need for the subsequent part of the talk, is hypernetworks. It is also a fairly simple paradigm. It is, so hypernetworks are just neural networks which output parameters for other neural networks. Basically, we have a main network or target network which has its own input and its own output, and we instantiate a hypernetwork which uses some context information, some conditional signal, which can be anything depending on your task at hand. And you predict the parameters for your target network. So you, in the simplest case, you directly plug them in. And since neural networks are typically differentiable with respect to their parameters, you can backpropagate through these predicted parameters and backpropagate further to the parameters of the hypernetwork. So if you have any questions, you can ask them, you can interrupt me and ask them along the way. But basically, so we've just covered the main building blocks, and now we can start discussing the main part, like how to build generative models over these neural fields, using the discussed paradigms like GANs, hypernetworks. So the first one, the simplest neural fields generator you can think of is the generator of 2D images, and a traditional image generator in the GAN-based framework, it is structured the following way. You have a latent code, a random noise, which you sample typically from normal distribution, and you pass it through a convolutional decoder to produce an RGB image in the grid-based representation. And the neural fields image generator would have a different structure. We also start with a latent code. Then we pass it through the hypernetwork MLP to predict the parameters for your neural fields MLP. Then we plug in these parameters into the MLP decoder, and we evaluate this MLP decoder in all the special, on some predefined coordinate grid of the predefined resolution. and this gives us an RGB image as a result. And the advantage of such a design, of such a decoder design, is that we can couple it with a conventional discriminator, image-based discriminator. So there is a long history in the community of developing 2D image GANs. That's why it feels reasonable to use as many existing established components as possible. And the described generator neural fields decoder could be easily combined with an off-the-shelf image discriminator. So basically, we have this neural fields generator, which produces the images in such a way. We have a set of real images, and we train a classical discriminator to classify them into real and fakes. So this keeps half of the traditional pipeline as is, which is an advantage in practice. But there are two disadvantages. So it is quite expensive, and in two ways. The first way is that just producing many parameters from the hypernetwork is memory intensive. And another problem is that producing high resolution images from neural fields MLP is computationally intensive. And that's why in our work, we invested a substantial amount of efforts into improving the efficiency, and we developed two ideas which are very natural. So the first idea is hierarchicity. So we evaluate earlier layers at low resolution to save computation. So the first layer starts with a very coarse grid, then we upsample it with bilinear or nearest neighbor upsampling, and concatenate and concatenate the positional information from a from a slightly higher resolution grid. Then we repeat this step again and evaluate the later layer on even a higher resolution grid, and so on until we synthesize the final RGB image. And another idea which we developed is sharing parameters between different neural fields MLPs to save memory. Because otherwise, if you always predict the full all the parameters for your neural field MLP, then you won't be able to build large scale generators. So basically, we allocate some amount of parameters as shared, then we predict with our hypernetwork generator just a small subset of unique parameters. We combine them together and plug into the MLP model. And this
Ivan,
allows...
may I ask a question here, or do you want?
Yeah, of course.
Yeah, so I understand your reasoning for why it would be hard to train if you're I haven't worked with hyper networks much to start maybe. And I understand your reasoning why you're saying, okay, training all parameters would be, or to learn all the network's parameters would be too hard. So what is really surprising to me, or maybe it will end up not being surprising, is the neural fields kind of overfit to one single scene, right? So by having shared parameters, what would you say, how much of it gets lost? Like it's a general concept. I know that first approaches will maybe not look as good as you would hope, but what is your intuition for having a big chunk of shared parameters? Are they like learning the logic of geometric structure? Yeah, I guess, what is your intuition for why this idea works?
idea of parameter sharing. So you mean?
Yeah, I
so
mean,
yeah,
what is the part that the shared parameters learn in your intuition? I guess I understand why parameter sharing works in general. I think I'm curious what they learn in the concept of in the context of neural fields.
That's a good question. To be honest, we didn't have any exploration on top of any analysis of how it influences which exactly parts it influences. And we had a quite specific mechanism of parameter sharing here. But you can consider that we learn just the modulation parameters of adaptive normalization. So basically for each layer, you predict a new mean and scale. So you predict a shift and scale for each layer with your hypernetwork. And it feels tricky to analyze what exactly is encoded here, because for different scenes it changes. I mean, it changes them too much. That's a good question.
Yeah, I think, no, I mean, your answer makes perfectly sense. I also would have no idea how to properly analyze what the shared parameters are doing.
Yeah, so the main problem is that it can change everything with you.
Yes, exactly. Exactly. Particularly if you use NGP style positional encodings because of the hash function.
To be honest, I'm somewhat skeptical about predicting NGP parameters because it is so they are very unstructured due to hashing. It feels like training a neural network to do sorting in some sense. So this kind of typically neural networks likes so if your input changes slightly, then the output should also change slightly. This is kind of a general idea of my intuition. But for instant NGP, it wouldn't be the case, I feel, due to a lot of discrete operations.
Yeah, fair enough. But I guess also for the positional encodings, we want exactly that, right? We want to be able to represent sharp edges.
Yeah, that's true. That's true.
So we lose that already when we want to do
yeah.
But yeah, I agree in general.
So yeah, and this design decision, it helped to improve the speed, to improve. So basically, these design decisions allowed to build an image generator which is more or less close to the conventional convolutional based generators like Stelgen 2, and they were even more efficient at training and inference time. And they had several interesting properties. One of the properties that you can do out of the box super resolution. Basically, you can evaluate your MLP decoder on a grid of higher spatial resolution, and it will give you it will give you super resolution capabilities out of the box. And also you can do some low resolution inference, low resolution synthesis with the generator by evaluating it on a grid of smaller resolution than it was compared to what it was trained on. And it will be cheap. So for a conventional convolutional generator, if you want to produce, so if you have a 1K generator and you want to synthesize a 64 by 64 image from it, you would need to do a full forward pass and then downsample. But for such an neural field based generator, you can synthesize it directly, and simply by evaluating in the special locations in the require special locations, and it will be much cheaper. And this could be used for previews or interactive editing. Another interesting, just curious property is that you can do some limited extrapolation with such a generator, and by evaluating in the positional locations outside the coordinate grid which was used during training. And you can push, I will slightly cover the idea of pushing this extrapolation capability to the limit, where we built a generator which is able to produce infinite continuous images. So basically, imagine that we have an infinite image, so I cannot display an infinite image here, but we also assume that we associate it with some coordinate plane, and then the idea is to position anchor latent codes on these coordinates plane, so to align the latent space of your generator with this special image space. And then we can train a generator to produce images in arbitrary locations. And for this, we use specially varying latent codes, and each pixel synthesized by such a neural field generator, it would use it would use a unique latent code which would correspond to linear interpolation between two nearby anchors. And this yields a specially equivariant generator. Imagine that we have, what that means is that when we shift an image, then it preserves its values depending so the predicted values do not depend on the offset which you use. So imagine that you have synthesized such an image, and we can assume that it is located in some coordinate center with the offset of 0, and then we generated an image with a slight offset, and then if we measure 2 pixel positions, if we measure the values in the same coordinate locations on this coordinate plane, then they would be equivalent. And this is the property which allows to do infinite synthesis at test time. So if you shift it further, then again, if you measure pixel colors in the same special locations, even if their relative positions in the image are different, they would still be equivalent to one another. And as a result, this allows to synthesize such infinite images at test time. So here, yeah, we were considering horizontally infinite images because, so for some technical reasons, but you can extend this paradigm for 2D infinite generation. Okay, now we will also cover the generation of videos in this neural fields representation. And the main idea is to treat videos as time continuous signals. So basically the traditional video representation treats videos as a 3D grid of RGB pixel values. So the traditional neural fields representation, it takes a 3D coordinate as an input. So the special 2D one and the temporal one. It is MLP based and it produces a single pixel per coordinate location. But in our representation, I lost the reference. Okay, so in our representation, we used a convolutional decoder for this neural field representation. Basically, given we take only a temporal coordinate as an input and produce the whole frame. And the use of a convolutional decoder allows to get rid of some artifacts. So because in our previous work where we were exploring an image neural field generator, we struggled a bit with special consistency of synthesized pixel values. And when you use a convolutional decoder, this eliminates this headache. And yeah, we produce the whole frame per a temporal location. And the architecture aligns closely with the conventional style Gen 2. So in the conventional style Gen 2, we have a constant input tensor. We have a convolutional decoder, which is modulated by a latent code. And the discriminator predicts discriminates the images from real and fake. And we took this image generator and with minimal changes using this neural fields paradigm adapted it for video synthesis. So basically, in our case, we had some temporal axis where we sampled locations from and encoded them with positional encoding. Then we were synthesizing frames independently from one another. So here they are. They are connected in a video through this temporal positional embedding. And after that, we pass them into the discriminator backbone independently from one another. And we use a simple concatenation. So we aggregate the temporal information from these frames just with a simple concatenation, while previous works were relying on 3D convolutions. And then we pass them into the discriminator head to classify into real and fake. And the discriminator is also modulated, is conditioned on the time differences between the sampled frames. And as a result, this allowed us to build a powerful, state-of-the-art back then. So it was staying a state-of-the-art for several months, which is good enough, I guess, for a video generator. And yeah, it was able to synthesize very long videos without diverging. So here is just the snapshot of the whole synthesis from a randomly synthesized video. And our generator was also able to keep some latent space manipulation properties of style Gen 2. Basically, you can project images into the latent space and generate videos and animate them. And can also do some editing based on clip using the style clip paradigm. Okay, so I need to confess that when I was restructuring my slides, I lost the references to the papers, but basically I can just tell you. So this work is from our INR-GAN paper from CVPR 21 with Salva Ignativ and Mohammed El-Hosseini. This one is from our Alice paper, aligning latent and image spaces with Grigory Sotnikov and Mohammed El-Hosseini. This one is our Stelgen V paper from CVPR 22 with Sergei Tudakov and Mohammed El-Hosseini. And this okay, maybe here I didn't lose. Okay, sorry for that. So yeah, here we now switch closer to 3D synthesis. Basically, a recent trend in generative modeling is generating 3D shapes from 2D images, and this assumes that you have a data set of 2D images and you want to synthesize 3D shapes. And these methods are currently GAN-based, and they typically follow the following structure. You have a latent code, a random noise which you sample, then you pass it through an hyper network or just a modulation MLP to predict the parameters for your neural fields generator. And this neural fields generator is evaluated on the 3D coordinates grid and predicts, synthesizes, so outputs and RGB. So it typically follows a neural radiance fields paradigm representation, and it synthesizes an RGB density field, which is then rendered with volumetric rendering at some small resolution. Then this render is passed to a 2D convolutional upsampler to predict an RGB image. And then together with real images, they are passed to the discriminator to be classified on real and fake. And this 2D upsampler is quite annoying because it leads to quite severe flickering. So there were several works to mitigate this, but ultimately the problem is still there. So the one issue is flickering, the other issue is that you learn the geometry in low resolution. And we developed Epigraph. It is a nerve-based generator which does not rely on a 2D upsampler and can synthesize radiance fields in high resolution. So it allows it to preserve view consistency and to learn decent geometry. And we did this simply by revisiting the conventional page-wise training. And so you can see that the view consistency is, so it has, you can call it the perfect multi-view consistency by design, since it is just the radiance fields which is being predicted. And also it predicts images, synthesizes it in high resolution. So yeah, the idea of our patch-wise training is the following. The conventional volume rendering is quite expensive in high resolution, and we take the idea of patch-wise training from graph and revisit it in two ways. First, we show that conditioning the discriminator on patch, scale, and location improves the performance, and then we also redesign the patch scale sampling strategy. Basically, patch-wise training works the following way. You have, consider that you have an image. It is again positioned on the coordinate plane, and then we subsample just a part of this, just a patch from this image, which has some random scale and random offset. And this patch is passed to the discriminator to be classified on real and fake. And this, the same exactly strategies is applied to rendering, to volumetric rendering of your 3D volume. And the discriminator is modulated on the patch parameters. It is conditioned on the patch parameters. So this compared to the
Sorry, I have a
baselines.
question.
Yeah.
So could you go back to the previous slide? So I'm just curious about what the motivation is about using beta distribution instead of the uniform distribution to sample the batch scale.
So basically, in our case, so in beta distribution, you can control how often you show patches of small resolution. So how often you can, so basically we showed that if you show, so if you synthesize small scale patches more frequently, then it helps to preserve the global consistency of an image. So in uniform distribution of graph, they were synthesizing these small resolution patches too frequently. And this kind of made the overall performance worse.
But instead of use beta distribution, you can actually limit the sample interval of the distribution, right? If you like to use uniform distribution, or you can use Gaussian distribution, but bounded with specific region.
So I'm not sure what you mean. So you generate patches of random scale. So sometimes they're like this, sometimes they're like this, sometimes they are like very large, but with a very large stripe. Okay. And so in graph, they use patch annealing, and initially they synthesize images with a very large stride, and then so this stride, the distance between two pixels, it is sampled randomly, and then you decrease the stride. You decrease the minimum possible stride which you can sample over time during training. And so basically we introduced one additional hyperparameter which you can tune, like this sampling schedule. And we showed that if you tune this hyperparameter, then you can improve the convergence and the final performance.
I see.
So it was a meaningful hyperparameter to tune. This is how I would describe it, which is related to how sampling the stress. Okay. Yeah, and but that was a good question. Thank you. So yeah, basically this allowed to generate high resolution images with which are view consistent, and do this quite efficiently. And also, since our framework was purely NERF based, it didn't use any 2D convolutions afterwards, then you can plug in existing techniques from NERF by simply copy pasting. And here you can see that you can do background separation. So you can just introduce an additional MLP from NERF++ to model the background, and here you render without this MLP. And the next project which we worked on is a 3D aware generator on interval datasets. Basically, modern 3D from 2D generators are designed for well-curated and aligned datasets, which have similar scale, zoom, and position, and they are also easy. You can easily define camera distribution for these objects, but in the wild data is very different, and that's why such generators are not applicable to it. And in this work, we developed several design techniques to improve upon this. So we start with our previous generator, epigraph, which has the following pipeline. So you have a generator which predicts, which outputs triplanes. Then you sample a camera parameters randomly and you volumetrically render an image. And the first change which we introduced is just using so training a discriminator to classify not RGB images, but RGBD images. And for fake images, we were rendering depth maps and concatenating them as the fourth channel. And for real images, we used LRS depth estimator. So basically, we converted each RGB image into its RGBD equivalent during the data preprocessing stage. And we were training the discriminator on RGBD images. And but this design, if you implement it naively, it has a catch. So and the catch is related to existing off-the-shelf depth estimators. So first, the ones which generalize well, they predict relative depth, and they are not perfectly accurate. So consider this real image as an example. If you estimate a depth map with layers from it, it looks the following way. And for example, the eyes, which feels close to one another, they are somewhat separated on the depth map, and a more noticeable error is the legs of the human, which are far away in the background. They are predicted to be closer than the tail of the dog. And that's why we introduced a depth adapter in the middle of this pipeline of our generator, of our synthesis pipeline, with some careful regularization strategies. And this helped this helped to avoid the generator from learning these depth artifacts from the rest, because otherwise the discriminator would force the generator to model and replicate its mistakes. Another strategy which we developed is knowledge distillation in the discriminator. Basically, one idea. So recently there appeared several works which explore this, and they typically do knowledge transfer through initialization. Basically, you take an off-the-shelf encoder, you initialize, you freeze it, and then you train a discriminator on top of its features. And it has two downsides. First, it restricts the overall discriminator's architecture, and another problem is somehow it didn't work for us for Stalgen 2. That's why we developed a different strategy for knowledge transfer into GANs. So basically, this is the conventional discriminator pipeline. You take an image, you predict, you classify it into real and fake. And then we estimated, we extracted features from ResNet at once before training, before the start of the training process. And then we were training the discriminator to predict the features of ResNet. So in this case, it was similar to knowledge distillation. And it doesn't restrict the discriminator architecture, because you can set up this additional head on any kind of network. And it worked well for Stalgen 2 and also could be easily combined with a patch-wise discriminator, which we had, and the discriminator which takes RGBD instead of RGB images. And as a result, it allowed us to build a model which synthesizes reasonable 3D shapes on ImageNet. So there are two problems that, so the main problem is with the background sticking, but still compared to existing baselines, it was a noticeable improvement. And if you explore the geometry, and then the EG3D, back then state-of-the-art generator, was predicting completely flat images. And then if you train EG3D with the wide camera distribution, then it starts to predict non-flat images, but with repetitive geometry. And in our case, the geometry was more fine-grained, and it was especially good on those ImageNet categories which were in domain for the depth estimator. So here are some additional samples from the generator, and I will briefly cover 2.5 more works for the content for 2.5 more works, which is state of the art right now in 3D synthesis. So the main one is Dream Fusion, and I guess you could be familiar with it already. So it was selected as the best, it received the best paper award on this ICLR. And it uses an off-the-shelf text to image diffusion model to generate 3D shapes from text in a zero-shot manner. It uses a neural radiance field representation as the underlying 3D representation, and it relies on a private, so it relies on Imagen model by Google and a ton of tricks to train. So this part is quite important because the community was struggling to reproduce the results with off-the-shelf, with open source stable diffusion model. And there are some, so in some subsequent works by NVIDIA, the authors argued that stable diffusion is inherently not a good fit for this, for such kind of tasks. And so Dream Fusion achieved really good results for 3D synthesis. So I would say that it was a huge surprise for the community on how good you can go for 3D synthesis with such a pipeline. And it is fairly simple at high level. So it uses a ton of tricks, but the high level idea is very simple. Basically, you instantiate your nerve MLP randomly. So the training pipeline looks the following way. You have a random nerve model, then you render an image from a random view. Then you refine this rendered image with the off-the-shelf diffusion model, and then the diffusion model is conditioned on your desired text prompt, the 3D shape you want to generate. And then you just compute the L2 distillation loss between those two images and backpropagate to the nerve parameters. Yeah, once again, there are like really a lot of tricks to make this pipeline work. And they were, until recently, I would say a month or a month and a half ago, there were no other works which would be able to get close to these results with stable diffusion. So the community was really struggling to get close to rival their quality. And the work which gave face to everyone was Fantasia 3D, released last month, I guess, and it achieves really good results. So, and it uses, so one of the key characteristics is that it is quite photorealistic. So they still do not show synthesis results on very difficult text prompts, which would have non-trivial global shape. But still, in terms of photorealism, it is even better than Dream Fusion. And it uses a different 3D representation, and it also uses an interesting trick of normal supervision with 2D diffusion. Basically, you pass to 2D diffusion not only RGB renders, but also your normal map renders. And Stable Diffusion somehow can guide normals. It can give a good supervision signal for your normal maps as well. And they also utilize a more sophisticated, a more physically plausible shading model to model better lighting effects. So the last work which I would like to cover is the current state of the art 3D generator on ImageNet. So basically, it uses 2D diffusions for novel view synthesis, and it trains two. At high level, it trains two diffusion models. The first one generates RGBD images unconditionally. So here the authors also rely on an off-the-shelf depth estimator, and the other diffusion model is trained to fill the holes from back and forth reprojection. Basically, given an image, you slightly change the camera, you change the camera position, you compute, you project an image onto the new camera, you project the pixel values onto your new camera plane, then you image plane, then you move the camera back, project again, and then you have your supervision. You have a input output pair for your diffusion supervision. And this model achieves very strong results on ImageNet synthesis. To be honest, I was really impressed when I saw their samples. So to conclude, the main idea behind neural fields, and yeah, by the way, so here they do not use any neural radiance fields. So it is just RGBD images and novel view synthesis. It is an interesting characteristic. So the main idea behind neural fields applications for different domains is just treating the underlying data as continuous, and there were several, so many subsequent design choices arise simply from this perspective. And with respect to synthesis tasks, it can give, so not only 3D generation, but also image and video generation. This perspective can give practically useful properties like infinite synthesis, infinite video generation. But when you apply it on a new task, for example, consider we are going to try to make it work on sounds. So there are some non-trivial problems to resolve. So first, it's not always obvious how to generate the parameters efficiently for your decoder network. Then the positional encoding is still an open research problem, even in the reconstruction tasks. And Also, in the default general framework, the output values are conditionally independent spatially independent from one another, and it might lead to worse spatial consistency. And at the end, I would just like to discuss some open problems in 3D synthesis. So the holy grail of 3D synthesis right now is building a foundational and preferably dynamic 3D generator. So, and it poses a lot of questions. So the first one, and the first one is what kind of data should be used to train it? Because, so for example, humans, they have binocular vision, they can move to collect multi-view information, but we still train 3D generators on single view 2D image datasets, and it might be a dead end in the long term. So I feel that we might need to explore data which has richer 3D information. Also, is it really okay that we rely on external 3D knowledge like depth, off-the-shelf depth estimators? Because you will be so it could be the case that your 3D understanding, if you rely on this external knowledge, then your 3D quality will be upper bounded by this 3D, for example, by depth estimators. And also a huge open problem is how to do dynamic 3D synthesis. So it is quite not a large subfield in NERF, even in NERF, so dynamic 3D reconstruction. And for dynamic 3D, for 3D videos, it is even, so the field is even smaller. There is just a handful of works. And there is no established backbone even for static 3D synthesis. And so I would even say that Dream Fusion, so right now the dominant paradigm is Dream Fusion, but 3D GANs are still very popular. And now with the work which I've shown on the previous, a couple of slides ago with diffusion models, there is now a new paradigm emerging. So there is no established paradigm even for static 3D synthesis. So dynamic synthesis would be even harder. Another problem is it's not clear it's really not clear what to do with difficult materials like hair or fabric or some bushes and leaves. So they might require some very tricky parametrization or great flexibility in your 3D representation, and then it will be harder to learn, or you would need even more data. And so this problem could be potentially solved just with scale. And another issue is incorporating more physically plausible shading models. So right now, even in the NERF literature, modeling such materials like liquids or modeling fire or smoke, it is a huge headache, and there is no established paradigm on how to handle them. And if you use a vanilla NERF, then your quality will be really low when you try to model such kind of materials. So in theory, this could also be solved, I guess, with scale, but here I am not so confident, to be honest. So in theory, your generator might be able to model all those kind of, it might be able to learn implicitly a physically based shading model, but it will be tricky. Okay, then I would like to thank all my collaborators who helped me and with whom I built several, like many discussed works together. And thank you for your attention. If you have any questions, feel free to ask. Okay, sorry that I guess I took a bit more than I expected. I'm sorry.
So lessons events talk, and it's very inspiring. So if there are any questions from Zoom, please just unmute yourself and ask a question.
I have a question. Hey everyone, how's it going?
Right.
So one thing that I kind of missed from the talk was like, what are your thoughts about aggregating representations that can be directly generated from stable diffusion? For example, I'm talking about 3D diffusion models. So like one way is to like use a static representation and then use multi-view and aggregate things there. Another one is to just generate a 3D representation through the diffusion model. So what do you think is a better way, might be a better way to do things?
That's a good but a tough question. To be honest, 2 months ago, I would say that we would need to generate 3D representations directly, but now I am not confident anymore, and so that work does exactly this.
This
So
one?
I guess yeah, this one, it is doing exactly what you've just said, but they train the diffusion model from scratch. So and their results are quite good. So
I was also surprised that these guys didn't require videos to do this. They just use single images. I believe just the whole ImageNet.
yeah, so answering your questions, to be honest, I don't really know. So I personally like generating 3D a bit more, but it is associated with so great amount of headache that I think that so it is really a headache to generate unbounded scenes, for example. You need a separate background model. Quite often you need a separate background model. I mean, in previous works, we typically use, and you need to make sure that it is quite powerful to model a difficult background. And that's why this approach of aggregating the results, it is really viable.
Makes sense. Yeah, yeah.
So what are your thoughts on...
Some people, sorry.
Yeah, please finish.
So to be honest, some people even believe that we do not need 3D. So in the long term, we might not need these 3D representations, for example, because if you have a 2D generator, for example, a 2D video generator, which implicitly knows 3D, all 3D perfectly, then you can model any 3D effects with this 2D generator. I'm not sure.
Yeah.
I mean, I would argue it's actually a legitimate view because we had the same discussion pre-neural nets about images, that in order to generate photorealistic images, do you need knowledge about individual objects? And now with the text-to-language generative models, it seems like, no, you don't need to explicitly encode knowledge about objects. You just train a big enough object model. But the question is, to what extent does this scale? I had another question. How much do you? I think it's a standard question I ask in these talks these days. Is how much do you still believe in GANs, whether they will survive, given how difficult they are to train? And yeah.
That's a very good question. So I more or less switched from GANs right now in my current projects, we were trying to improve the low-level backbone for 2D diffusion, and it's not, it's quite tricky to do this. But anyway, so there are some smart people who still believe in GANs, and from my perspective, diffusion models are not as easy to train as well. So I wouldn't say, so my take is that for image synthesis, GANs are fairly stable, because I mean, if you take the state-of-the-art GANs, the one like style GANs, but the problem is mode collapse. So mode collapse is still an issue. And I would say that if you invest really a lot of efforts into GANs, you can achieve a similar quality to diffusion models. And you will not suffer from training instability much. But so the mode collapse might still be an issue. So answering your question, the main problem with GANs is mode collapse, and the overall framework is now more or less clumsy, I would say, not training instability. And for some tasks, it is still viable. For example, for one-shot synthesis on faces, GANs still achieve the best quality. In practical applications, they are still being used. But yeah, since the whole world, I mean, the whole community is now moving to foundational models, GANs are having a tough time because of this, I would say, mode collapse issues would be the main problem. Also, to be honest, looking at the diffusion models, I think that one of their main powers is multi-stage generation. So for example, for object detectors, like two-stage detectors outperform one-stage detectors, right? And you can treat GANs as one-stage synthesis models, while diffusion models are multi-step. And this is really a big deal for complex data sets. So I think that if I think that GANs have trouble because of mode collapse and because they are one stage. And the second problem, it is a technical problem. You can resolve it.
Yeah, makes sense. Although in multi-stage detectors, the two-stage are like qualitatively very different stages. In diffusion models, it's more like a multi-resolution. Yeah, I'm not sure if that's like correct way of putting it, but yeah. Whereas in multi-stage detectors, it's like proposal generation and selection.
Yeah. But yeah, I agree. To be honest, I do not think that diffusion models will survive in their current form. Like in 5 years from now, I think they would be somewhat different.
Yeah.
So I think
is there any more questions?
Sorry, I had a bit more of a specific question. First of all, thanks for the talk. I think it was great. I'd like to go back to the moment where you were talking about like continuous for time, but discrete for spatial representations. Yeah, exactly.
Wait a second.
Yeah, so I saw that you are using positional encoding for the time dimension. Could you explain a bit more about the motivation behind positional encoding for time specifically? Because like PE, as far as I grasp, is you can capture very high frequency details in that dimensions, but along the time dimension, maybe you wouldn't expect so much variation, right? Especially in the smaller scales.
Yeah, that's true. So you mean there is some temporal special correlation, but so in our case, the main motivation of going from this design choice towards this design choice is to eliminate the headache with special inconsistency between pixels here. Because in our previous inorgan work, we had an issue that, for example, a pixel value here could be unnaturally too different from a pixel from its neighboring pixel. So, because in a convolutional decoder, neighboring pixels communicate with each other through convolutional layers and through upsampling, through interpolation during upsampling. So they are conditioned on the same special values in some sense in these two transformations. And in purely neural field decoder, they are conditioned only on the same global latent code, which leads to worse spatial consistency. I'm not sure. So that's why we went from this.
Yeah.
From this part to this one. But
I think
sorry.
I think the motivation there was clear to me. I was maybe it was one more slide after this. It was, I think, when you were when you had the architecture of with the GAN, the discriminator and everything.
Yeah.
Yeah, exactly. So here you were applying PE to the time dimension, and I was just trying to find some motivation behind that specific one.
Of applying positional encoding here?
On the time, yeah, exactly.
Yeah, but the alternative would be to pass just a single scalar value, right?
Yeah.
And
yeah,
sure. So for this, a single scalar value, the problem is that the generator, it would have the same issue as for special, like XY special positional impedance. Similar values, they might have, so the input will be too smooth. And if there is a drastic movement in the output, for example, I don't know, so for phase generation, someone might sneeze, then the generator won't be able to. So what positional encoding? I have a slide actually on this. So the intuition behind positional encoding is that it allows the generator to model sharp changes in the output, as Igor said. And if you have temporal sharp changes, then you really need positional encoding for time. But if your videos are very smooth, then yeah, we could go without any positional information.
Yeah, that makes sense. Thank you.
So yeah, I do have a slide. Okay, it's quite long. Sorry. Yeah, okay.
No,
Yeah,
think the
so
idea
answering
makes
the
sense.
question again, just to model sharper changes in the output, to make the generator be able to model sharp changes, temporal sharp changes, like quick motions. And also another reason is that we used relative positional embeddings, and this is a too technical detail, but that's why I didn't cover it. But basically to generate, if you want to generate infinite videos, you need some relative positional embeddings, because otherwise you will start feeding like infinities to your generator if you use just the time, the raw time scalars.
Cool, thank you.
Yeah, thank you for your question.
So is there any more questions from Zoom? If not, let's thank Ivan again for his inspiring talk. So this is the end of the seminar today.